Alright, today we're going to talk about colligative properties. And colligative properties are based on the vapor pressure lowering. If you add a non-volatile solute, that is a solute that will not evaporate, to any liquid that will evaporate, the vapor pressure will be lowered. And the reason the vapor pressure will be lowered is those non-volatile solute particles are actually blocking the solvent particles from being able to leave the surface of the liquid and transition into the gas phase. Okay, so we have a law that takes care of this for us, and that is called Raoult's law, and that means that the vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Let's recall that the mole fraction is equal to the moles of one portion of the solution to the total number of moles. And in the past, we have used the moles of the solute. Now we're using the moles of the solvent over the moles, total moles of the solute plus the solvent. All right. Now this is important because some solutes break into more parts than others. If you have a solute that is an electrolyte, then it will break into its ions. For example, sodium sulfate, when it is dissolved, breaks into 2 sodium particles and 1 sulfate particle. That will make 3 times the blocking power of something that does not ionize. Something that is a non-electrolyte, like a molecular compound like glucose, will just block in one piece, whereas a sodium sulfate will block in 3 pieces. The Van 't Hoff factor tells you the number of particles that are in solution. Okay. An ideal solution is a solution that obeys Raoult's law. Now, an ideal solution depends on the attractive forces between the solute and the solvent. So if you have a solution where the particles of solute are attracted to the particles of solvent, that means they will be attracted to each other, and the solvent won't be able to leave the solution into the gas phase because of the strong attractive forces holding it together. That would be a negative deviation from Raoult's law. If you have a vapor pressure that is greater than predicted, that would mean very weak attractive forces between the solute and the solvent. So many of the particles will be nothing will be holding the solvent particles from evaporating except for the blocking action of the solvent. The solute. All right, let's calculate the vapor pressure of a solution fairly quickly. It says calculate the expected vapor pressure at 25 degrees C for a solution prepared by dissolving 158 grams of table sugar into 643 cubic centimeters of water. Let's remember that a cubic centimeter is the same as a milliliter, and the density of the water at 25 degrees C is 0.9971 grams per cubic centimeter, and the vapor pressure of water at that temperature, which is the solvent, is 23.76 torr. Okay, now we remember that we're using Raoult's law, so the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure. And so the vapor pressure of the pure is given to us we need to find the mole fraction of the solvent. First thing we need to do is find the number of moles of the solute that is blocking the water. So the number of moles of the sugar are equal to 158.0 grams, and 1 mole of sucrose has a molar mass of 342.3 grams. That will give us 0.462 moles of sugar. Before we can figure out the moles of water, we have to figure out the grams of water. We have the density, 0.9971 grams per centimeter cubed. We would like to know the number of grams, and we do know that the volume is 643.5 centimeter cubed. So the number of grams is equal to 641.6 grams. To find that, the number of moles, we use the molar mass of water, and so we have 35.64 moles of water. We would expect that the sugar would not do a very good job of blocking the water from evaporating, so we would expect, as the answer tells us, there is not a huge difference between the vapor pressure of the pure and the vapor pressure of the solution. Right. So the vapor pressure, we have to find the mole fraction of the solvent, and that would be 35.64 moles divided by the quantity, 35.64 plus 0.462, and that gives us a mole fraction close to 1.987, because there's a lot more solvent than there is solute. So the vapor pressure of this solution will be 0.987 times the pure, which is 23.76 torr, and that gives us the published answer of 23.46 torr. You may use any pressure unit that you would like in this equation. Okay, now we're going to talk about a solution that has an ionic solvent in it. So what we have here is the solute is sodium sulfate. So we would like to know the number of moles of sodium sulfate equal to the mass that is put into solution. They give us the molar mass. And we find that we have 0.246 moles of sodium sulfate. Now we have to remember that the Van Hoff factor, as we saw before, for sodium sulfate is 3. Sodium sulfate will, in solution, break down into 2 sodium ions and 1 sulfate ion. So if I have 1 mole of sodium sulfate, I will get in solution, I will get 2 moles of sodium ions and 1 mole of sulfate ions. So if I have 0.246 moles of sodium sulfate, that will give me 0.246 times 2 in the sulfate ions. That would be 0.492 moles of sodium ions, because each sodium, there are 2 sodium ions, plus the 0.246 moles of sulfate ion. So totally, the number of ions I have that are blocking the water from evaporating is 0.738 moles. The number of moles of water equal to 175 grams of water is equal to 0.975, 972 moles. The mole fraction of the water is equal to the moles of the water divided by the moles of the water plus the number of moles of ions, and that mole fraction is 0.930. So the vapor pressure of this solution is equal to 0.930 times the vapor pressure of pure water, 23.76 torr, and that gives us this answer right there. Alright, now I want to talk about what happens when we have two liquids, both of which are volatile. They will both create a vapor pressure over the liquid, and we need to account for both of them. Essentially, you find the vapor pressure of both of them and add them together. Now, generally, we call the solute the one that is in lesser quantity than the solvent. So let's figure this out. I need to know the number of moles of the acetone equal to its amount in the solution. And we find we have 0.1 mole of acetone. And then we have to find the number of moles of chloroform, which is acting as the solvent here. And there's also 0.1 mole of the acetone. So the way to then proceed is to figure out the mole fractions of each. So we have 1 mole of the acetone over the moles of acetone plus the moles of chloroform, and we can see that will give us a mole fraction of 0.5. And we can also see that that's what's going to happen with the chloroform as well. So the vapor pressure of the acetone will be its mole fraction times the vapor pressure of the pure, that's 345, and that is equal to 172.5 torr. And then the vapor pressure of the chloroform is equal to its mole fraction, also 0.5, times the vapor pressure of the pure, 293, and that will be equal to 319 torr. Together, they make up the vapor pressure of this solution, and the vapor pressure of this solution is 319 torr. Ideally, it is 319 torr. The vapor pressure was measured at 260 torr. 319 torr does not equal 260 torr. So this is not an ideal solution.